actually probably won't take too awful long because some of this stuff we already covered in class. But I'm still going to go through it anyways because you never know who might need it again. So this is all on chemical reactions. So today's is on chemical reactions. Tomorrow's is kinetics. Then the following Monday is like thermochemistry, thermodynamics, so like heat, delta G, delta S. And then Tuesday is equilibrium. Dun, dun, dun. Yeah. So then this gives you the big ideas. So if you need one of these, it goes through and shows the different big ideas. So kind of like the checklist for the learning objectives. And so, so this just kind of shows your general chemical reactions, right? Looking at particle diagrams. Okay, so types of chemical reactions. If you remember, we talked about these. We have combustion, so you have any hydrocarbon plus oxygen. Always yields CO2 and H2O. Oxidation reduction. You have your oxidation numbers change. So make sure that you can assign oxidation numbers. So just kind of like ask yourself, can you still assign oxidation numbers, and looking at whether it's an element or whether it's in a compound. Your oxidation numbers have to change for it to be an oxidation reduction reaction. Electrons have to be transferred, which means your oxidation numbers have to change. Acid-base, which is your neutralization reaction, you have a proton being transferred. So one way or another, you have a proton being transferred. And sometimes an acid-base reaction could be like a conjugate base reacting with an acid. And then you have precipitation reactions, which is when you form a solid from two solutions. Precipitation reactions and acid-base reactions are typically when you see your net ionic equations. And so you have to be able to write your net ionic equations for your precipitation and your acid-base. Precipitation reactions also are what take into account gravimetric analysis. So we talked about that a little bit in class, but then also during Big Idea 1. Gravimetric analysis is when you precipitate out something, and then you can use stoichiometry to figure out what your concentration was initially. So this was actually for response question 2 years ago. So you have potassium sorbate, which is this equation right here. It's commonly added to diet soft drinks as a preservative. A stock solution of the potassium sorbate of known concentration must be prepared. A student titrates 45 milliliters of stock solution with 1.25 molar HCl. Value for Ka is given, but part A of this says write the net ionic equation for the reaction between the potassium sorbate and HCl. And so what you can do is you can set this up just as your normal reaction. So your potassium sorbate plus your HCl, draw an arrow, create your products, but always go back. This says net ionic equation. So if you do potassium sorbate plus HCl, this is going to be an acid-base reaction or double replacement. It looks like the same thing, but the acid donates a proton, and then your K will actually come with the Cl minus. So if you think about this, will I break up potassium sorbate into its ions? Should I break it up? Yes. Why? Because K, right? It's a soluble ionic compound, so we'll break this up into its ions. What about HCl? Why? Strong acid. So you're actually going to break up both of these into its ions as the reactants, and then as the products, your K plus and your Cl minus is a soluble ionic salt, so that breaks up. But then this HC6H7O2 stays together. How do I know that this is a weak acid? Right, not one of your 7 strong. How do I know that this is just an acid in general? Starts with an H. Okay.
Are you expected to label states of matter?
You don't have to. Like in this case, it doesn't do it for you. I would say if they give you the states of matter, label those, like label the ones that you know. But in terms of the products, like for this weak acid, it doesn't give you the state of matter. For KCl, you would know that it's aqueous because K plus. is always soluble, and so you would make that aqueous. But in terms of this one, you don't have to worry about the ascorbic acid. But it does show you your net ionic equation, and that's just the 1 point. So then balanced equations, again, just knowing the difference between the complete molecular, which is what you would normally think of as a balanced equation, complete ionic when you split up everything that's soluble, and then your net ionic. Just remember the only solubility rules that you have to know are potassium, nitrate, ammonium, and sodium. If they want you to know any other solubility rules, they will tell you. So they would tell you maybe that like AgCl is a solid, or maybe they would tell you that I'm trying to think of one, like magnesium sulfate is aqueous. Right? If they would tell you magnesium sulfate is aqueous, then you know that you can split it up into its ions because it's soluble. But the only ones that you absolutely have to know are potassium, nitrate, ammonium, and sodium. Okay, so then this next slide goes through the making predictions, and this is the one that we looked at in class because we had talked about how we did this in lab. So when you have solid copper carbonate and you heat it up, remember that whenever you have a carbonate and you heat up a carbonate, whether it's carbonic acid, copper carbonate, sodium carbonate, you always get CO2 gas. So whenever you're given a carbonate, anything with CO3, and you heat it, you always will get CO2 gas. And then it asks about evidence of a chemical change. And so we had talked about the ways that we can tell that a chemical change occurs. And in this case, what do you form in this reaction? Gas. Right, so typically we see a gas being produced by looking at the bubbles. And then if we see a color change as well. And in this case, copper 2 oxide is like a brown-black color. So we would see that color change. And then percent yield we talked about in class. And so remember, percent yield is how much of what you were supposed to collect did you actually collect. Right, so like you always have to figure out how much did you actually get in lab and how much were you supposed to get. And that how much you were supposed to get is the theoretical yield. So when you find percent yield, it's always actual, which is what you collect in the lab, over theoretical times 100. You should not get a number that's more than 100%. Okay? If you did, then something may have gotten messed up somewhere. But theoretical yield is always just stoich. So theoretical yield, you just do some stoichiometry. So you take your copper carbonate, you go to moles, use your mole ratio to go to CO2, go to grams, and then actual over theoretical times 100. Some lab-based questions. How could you improve your percent yield? Well, make sure you have a pure solid that you're starting with. And then you can always improve the procedure by reheating until you make sure that there's absolutely no water left, because that's a big thing.
How many lab-based questions are there?
That's a good question.
It seems like there's a lot on these.
There didn't used to be as many. 2 years ago, there weren't any. Last year of the free response, 3 of them were lab-based. So number 3 of the free response, that was a stoich lab-based question, which also kind of threw in some electrochem, and we're actually going to go over part of that in this review. And then there was one with the burette, and you had to read the amount of volume, and you had to use that for a titration, and so it was kind of like it gave you a picture. And then there was a kinetics-based question. I think that was on last year's test too. So there were 3 of the 7 were more lab-based. Only one of them was really like, number 3 was really the only one where it was like, how could you improve this? What could you have done wrong? The other 2 were just like, here's a hypothetical experiment, use this information to find concentration or something like that. And I'm trying to get to as many free response questions as we can, especially with the practice exam questions, because those have more of the lab-based ones too. So limiting reactants, we talked about limiting reactants in class. So I fixed this dimensional analysis limiting reactant slide from what we did in class, because if you remember when we looked at identifying the limiting reactant, it was like it looked at how much of the other product you had. It was very confusing. So I went back in and I actually changed this to how we normally do limiting reactant problems. So the biggest thing that I can say, because more than likely it's not going to outright say what's the limiting reactant. It might, and if that's the case, that'll be good. But more than likely it's going to say, you know, you have 15 grams of aluminum sulfide, you have 10 grams of water, how much H2S can you form? So it's going to kind of skip this identify the limiting reactant. If you are given amounts for more than one reactant, start by identifying the limiting, even if it doesn't say to. So kind of two things whenever you have a stoich problem. First one, always go to moles. That's going to help you. All right, so always go grams to moles. But then if you are given an amount for 2 or more reactants, you have to find the limiting. And so what I did here when we identified the limiting is I took the amount of aluminum sulfide and I went to amount of H2S formed. I did the same thing for water. I went from the amount of water that we start with to the amount of H2S that we could form. And then H2O is limiting, right? Because H2O can form the smaller amount of product. That means that water is what we're going to run out of first. So the limiting reactant isn't necessarily what we have the least amount of. It's the one that's going to run out first. And so that in this case is water. And then for part B and part C, these are just stoich questions. So part B is actually what we found in part A. Right? It's just, you know, I rounded a little bit in part A. But the maximum amount, you always, always, always do calculations with your limiting reactant. And then how much excess reactant is left. What we have to do is we have to figure out if we use 10 grams of H2O, how much aluminum sulfide would we need? So that's just going to require us to go back and do one more stoichiometry calculation to figure out the excess reactant. And then I talked about going through and solving with BCA tables. You don't have to do this. This is just another way that you could solve it. So before, change, and after, you just take your number of moles that are in here. You look at which one you have more of, less of. If you like stoich, go for the stoich. Experimental design. This is one that we did in class, and we talked about this one. We have pure copper that's heated in oxygen. It says design an experiment to determine whether the product is CuO or Cu2O. And so what we can do is we can find the mass of copper, heat it up, figure out what that mass is. And then really what we need to do is look at our mole ratio of copper to oxygen. If it's a 1-to-1 ratio, it's CuO. If it's a 2-to-1 ratio, it's Cu2O. So always compare your moles when you're looking at empirical formulas. That's really what you're doing in this one. And then for this decomposition, it's going to be a similar way. It says illustrates conservation of mass, so the mass after should be equal to the mass before. Data analysis question. So this was one like, it was the 2014 number 1 free response question from last week. It had like the mass of the Ki tablet, and then it was the one that we did in class. That one's kind of like this. So you have tin, crucible plus the solid after the heating, after the second heating, and after the third heating. And then it's going to just ask you questions about this. So how can you use this data and the law of conservation of mass to determine the formula of the product? So this is just kind of going through and reviewing some lab techniques. So you can actually take the mass of the crucible after the final heating. So always use, if you're heating something up, always take the mass after the final heating, because what's the point of heating the crucible and the solid so many times? Get rid of all the water. So you actually want to take the mass after the final heating to make sure that all the water's gone, and then we'll actually be able to figure out the mass of our solid. And then in this case, it walks you through step by step. So find your moles of tin, and then figure out how much solid you have, figure out your amount of oxygen, and then like before, do an empirical formula. So compare your moles of each. So here's moles of oxygen, here is moles of tin, and then you have your, let's see, here's my moles of tin. divide by the smaller number. That's going to give you SnO2. So this is more of a lab-based question for finding an empirical formula. Always go to moles and compare your moles. Okay, so now kind of moving on to acids and bases. We really only deal with Bronsted-Lowery theory of acids and bases. So if you remember, acid is a proton donor, base is a proton acceptor. Your proton is typically H+. But then we can deal with conjugates. So if you have an acid that donates a proton, from the left to the right side, we would see its conjugate base. So we always have an acid-base pair, no matter what. You have an acid-base pair on the left, and then from the left to the right, you have an acid-base pair. And then the base, once it accepts a proton, it becomes the conjugate acid. So if you just remember that the acid always has to have one more H. So if you look at this, right, hydrogen fluoride in this case acts as an acid. It donates its proton to water, and then it becomes F-. And then ammonia, if you remember, ammonia is the same as NH4OH. So like ammonia and ammonium hydroxide are actually the same. But ammonia is a weak base. And then water can act as both an acid and a base, and that's called amphoteric. So water, you can also have like HSO4- like we talked about in class today. HSO4-, if it has a negative and it has a proton to give, it can be amphoteric. So HSO4-, H2PO4-, HPO42-, right? Those all are amphoteric. It can donate an H, but it also has space to accept an H. Yes, yeah, diprotic. So like the conjugates of a diprotic or a triprotic acid. Yep. So here's another example. This was one from last year. So this was last year's free response question. So a student designs an experiment to study the reaction between NaHCO3 and HC2H3O2. So sodium bicarbonate and acetic acid. The reaction is represented by the equation above. Student places 2.24 grams of sodium bicarbonate in a flask and adds 60 milliliters of acetic acid. The student observes the formation of bubbles and that the flask gets cooler as the reaction proceeds. Part A says identify the reaction represented above as an acid-base reaction, precipitation reaction, or redox reaction, and justify your answer. So when you answer this question, you can do one of two things. You can look at it and try to recognize it as one of these three types. It can only be one of these three. Or you can use process of elimination to justify. So, like if it was a precipitation reaction, what should be formed? A solid. Was a solid formed? No. So it can't be precipitation. If it's a redox reaction, what has to change from reactants to products? Oxidation numbers. And so we could go through and we could assign these. So like Na here is +1, Na is +1. I'll give you this hint. Here is acetate. Here is acetate. None of those numbers are going to change. If you have a polyatomic on the left and the right, those oxidation numbers always stay the same. And then we could look at CO3 here. I'll just tell you all the numbers stay the same. Right? And you could work through and you could label all of them, but all the numbers stay the same. So can it be redox? No. So it's going to be acid-base. Now here's a way that you can tell. This is acetic acid. If you look from the left to the right, okay, this HC2H3O2, this loses an H. Right? And notice this isn't an anionic equation. Tisk, AP. But this H comes over to this HCO3-. And if you remember, I told you whenever you form H2CO3, it's unstable and it breaks down into H2O and CO2. So this is an acid-base reaction. So in this case, you got 2 points. One for saying it's acid-base, and then the second point came from a justification. And notice on these scoring guidelines, you could have one of two justifications. You could say the weak acid donates a proton to the weak base, which is HCO3-, Or you could say what we said. No solid precipitates, so it's not precipitation. None of the oxidation numbers change, so it's not redox. Therefore, it's acid-base. And that was 2 points. Okay, so then coming back to redox reactions, all this information at the top essentially says you have 2 types of reactions. You have reduction and you have oxidation. Reduction reactions are when your oxidation numbers go down. So you go from 0 to -1 or +1 to 0. It gains electrons. And then when something is oxidized, it loses electrons, and so its number increases. So whether you use Leoger or oil rig is up to you. But that will help you. And so the first thing, again, is to think to yourself, can you assign oxidation numbers? If not, look back. We just did redox a couple weeks ago. Look back at your notes on assigning oxidation numbers. When you are looking at redox, always split it into half reactions. Don't ever forget to split it in half reactions. If you have a charge on the left and you have a charge on the right, like Zn2 plus, I don't know, Ag goes to Zn plus Ag plus. Split it into half reactions to balance, because that will also help you to figure out how many moles of electrons are being transferred by looking at the half reactions. Okay, so always split it up because your redox reactions show how many electrons are being transferred, and so that's going to be the best way for you. And remember, in order to add them up, your electrons have to equal. All right, so in order to add these 2 up, what would I have to do? Multiply the oxidation half reaction by 2. Right? Your electrons always have to equal for you to cancel them out. Okay, so here's sample question. So zinc ions will react with aluminum metal according to the following equation. Based on this chemical reaction, how many moles of electrons would be transferred when 1 mole of zinc 2 plus ions are consumed? So split it into its half reaction. So split, if you're looking for zinc 2 plus, split this into its half reaction and figure out how many electrons it takes. So to go from zinc 2 plus to just zinc, you want just 1 mole of it. So if you have just 1 Zn2 plus going to Zn, how many electrons would be transferred?
2.
Okay. Just 2. Because you only want 1 mole. Now if you had 3 moles, then it would be 6 electrons. But you just want 1 mole of zinc. So for each 1 Zn2 plus, 2 electrons are going to be transferred. Okay, then redox titration. So we did this lab in class where we looked at titrating potassium permanganate and oxalic acid. And so redox titration just lets us determine the concentration of an unknown substance by titrating it with a known concentration of typically potassium permanganate. And the reason we use potassium permanganate is because it's purple, so we don't have to use an indicator. So a common example is using potassium permanganate, and then you guys actually did the unknown iron 2 compound. That's what you started with because you did this over 2 days. And so in these redox titrations, you have one that's known, one concentration is known, and one is unknown. So the whole point of any titration, whether it's acid-base, whether it's redox, is to determine the concentration of something. In this redox titration, if you notice, it went from clear to pink. And the reason that it does this is because as you add potassium permanganate, usually the permanganate, as it gets added down here, reduces to Mn2+, which is clear. But once you've titrated everything in here, your Mn is no longer getting reduced. Well, since your permanganate's purple, that's why it turns your solution kind of a pinkish purple. In any redox titration, you just do stoich. You use your balanced equation, and you do stoichiometry to figure out moles. So if you know how many moles of KMnO4 you added, which you can use by using volume and concentration, then you can do some stoichiometry to figure out how many moles of iron or how many moles of acid you started with. Okay, so then evidence of chemical change, and we talked about this. Here are ways to tell that a chemical reaction occurred. So we make a gas, we form a solid, we change color, we have some heat, or we need heat, right? One of the two. Either it's released or it gets colder, so it absorbs heat. And then physical changes that we might see bubbles, and this particle diagram just kind of shows what it looks like as water boils. With this common misconception, and who knows if they'll ask it as a multiple choice question or not, but it's a very common misconception that boiling water makes H2 and O2 gas. Right? Water is water. So water and water, it's the same thing. When you boil water, you're just creating steam. Covalent bonds are not broken during phase changes. Only hydrogen bonds are broken. So don't fall for that trick if they ask it in a multiple choice question, what is broken when water boils? You should say hydrogen bonds and dipole-dipole and dispersion, but not covalent bonds. Okay, so some energy changes. This is just looking at general exothermic and endothermic. When bonds are broken, think about a stick. If you have a stick and you want to break a stick in half, it takes energy. You have to put energy into the stick to break it. Right? It's an endothermic reaction. So breaking bonds is endothermic. When you form bonds, so you bring like two magnets together, when you bring two magnets together, it happens on its own. That releases energy. So breaking bonds is endothermic. Breaking bonds takes energy. Forming bonds releases energy, and that's exothermic. And so then looking at these energy diagrams, in exothermic reaction, the products have less energy than the reactants. And so from your reactants to your products, you actually release energy. Because since your products have less energy, it has to be released. For an endothermic reaction, it has to absorb energy, so your products are going to end with more energy. Always looking at these, and we'll look at these reaction diagrams more in kinetics tomorrow, but activation energy is the energy it takes for a reaction to proceed. So that's this hump that you have to get over. And then up here at the top, if you remember, is the transition state or the activated complex. Okay, so now looking at cell potential. So AP tends to use the term galvanic instead of voltaic, but they're the same thing. Galvanic and voltaic are the same. Both take place in a spontaneous reaction. So a galvanic and a voltaic cell are the same thing. But in a galvanic or a voltaic cell, it's a spontaneous reaction, which means that your E is positive. Right? Your cell potential is positive in a voltaic cell. And so in this question, it says the following is based on combining the three different half cells listed below. So you have X, Y, and Z. So here, X is 1 and 2, 2 and 3, 1 and 3. So it says, what's the cell potential of cell Z? Okay, so what we have to do is we need to combine X and Y so that we form Z. So what do we need to do to X or Y to form Z? Like, what do I have to do to these reactions to make this half reaction? Okay, multiply Y by 2. If I multiply all of these by 2, do I have to do anything to E? No. Remember, the only thing you ever do to E is flip the sign. So I'm going to multiply reaction Y by 2. What do I need to do to X? Okay, flip it and multiply by 3. So what do I have to do to E naught of the cell? Change the sign to negative 0.94. Okay, because if you multiply by 3, that doesn't matter. The reason that you don't have to multiply is because your cell potential is based on how many electrons you transfer. We just changed the sign of this 0.94. And then what do we do to our E's? Add them up. So what's negative 0.94 plus 1.54? 0.6. Right, so because when you flip this, when we flip potential or cell X, we just change the sign. Multiplying doesn't do anything. Some other things with galvanic before I forget. So batteries, so galvanic cells, have very, very high equilibrium constants, very large equilibrium constants, because it's a spontaneous reaction, so it's going to proceed on its own. And so your galvanic cell has a very, very high equilibrium constant. It also has a negative delta G. So anytime you have a galvanic or a voltaic cell, you have a high value of K, very large K, and a negative delta G. When you are at equilibrium, when you are exactly at equilibrium, the voltage of any cell is 0. So if you are at equilibrium and your voltage is 0, your cell is dead. So you don't want to be at equilibrium because that means that your cell is not going to work. So a battery is going to have a very high equilibrium constant, very large equilibrium constant, a very negative delta G. But the closer to equilibrium we get, the lower the voltage becomes. Because since at equilibrium voltage is 0, the closer to equilibrium we get, the lower the voltage. So it's bad to reach equilibrium in a voltaic cell. And then the further from equilibrium we are, the larger your value of cell potential. So you want to be far from equilibrium to have a really high, really strong battery. Okay, so then redox reactions and half cells. So here's another one. In galvanic cells, X and Z. Okay, so in galvanic cells, X and Z, which of the following takes place in half cell 1? So here's half cell 1, right? Here we have half cell 1. It's the tin half cell. So in cell X, what happens to the tin? What's the oxidation number here?
0.
What's the oxidation number here?
2 plus.
So it goes from 0 to 2 plus. It becomes more positive. So it's oxidized. In cell Z, it goes from 2 plus to 0. So what happens? It's reduced. So we need to find the answer choice that says in cell X it's oxidized, in cell Z it's reduced. That's C. Okay, so now this actually comes back to free response question number 3. If you already did this, then you'll have these answers. But if not, this is useful. So free response question number 3 of last year's test drew very heavily from big idea number 3. And this really focused on the back of the free response question. And so it said, while cleaning up after the experiment, the student wishes to dispose of the unused solid I2 in a responsible manner. The student decides to convert the solid I2 to I- anion. Student has access to 3 solutions: peroxide, Na2S2O3, and Na2S4O6, and the standard reduction table shown below. Which solution should the student add to I2 to reduce it to I-? So let's start with what this is asking us. So this says we want I2 to reduce down to I-. So we want to look at this middle half reaction. This is the one that we want to take place. Oh, my phone. Interesting. Oh, well, it's fine. It's whatever. So we want I2 to reduce to I-. So this middle half reaction is the one that we want to focus on. When you focus on cell potential, these are the standard reduction potentials. What does it mean if we have a higher reduction potential? It's more likely to reduce. So if we want I-, we want this middle half reaction to take place. This needs to be the highest reduction potential that we're dealing with in the reaction. Okay, so let's keep that in mind. This is the number that we want to be highest. We can eliminate this peroxide. Okay, we can eliminate this peroxide because we don't have O2, we have H2O2. So if H2O2 were a reactant, we'd have to flip this, and we're not going to worry about that at all. We're just comparing these three numbers. This 0.54 is the number that I want to be the highest. So I'm going to keep that in mind. So then I'm focusing on this top number, right? This top half reaction. This is the reduction half reaction that I want, this middle one. In order to have a reduction half reaction, what else do you need? An oxidation. What do I need to do to this top half reaction to get oxidation? Flip it. When you flip it, what's your reactant? This S2O32 minus. That's what we need to circle. Okay, because, oh, and if you notice, it says, include a calculation of E naught for the overall reaction. This is the reduction half reaction that we want. In order to have reduction, you have to have oxidation. This tells you up here that these are the standard reduction potentials. So if this is reduction, this one needs to be oxidation. We're going to flip it. If I flip this reaction, what do I do with E? Flip it, make it negative. And then how do I find the overall cell potential? Add the two together. So Na2S2O3 is what we're going to use to reduce I2 to I minus. Really what this is asking is, what should we use as the reducing agent? It just didn't use the term reducing agent. So this wants to know what should be the reducing agent in this reaction. Well, that's going to be whatever needs to be oxidized. And so in part E of this, you get 1 point for circling the Na2S2O3. And then the other point, it says, earned for a correct justification. Notice it says, justify your answer and include a calculation of E naught. Well, your calculation can be your justification. Right? Reaction between S2O3 and I2 is thermodynamically favorable. It's spontaneous. Because E naught for the reaction is positive. And then delta G is negative. Nope. Nope. I would say that if you are dealing, whether it's E or delta G or whatever, if your E is positive, just make a note, like in your justification, like it's spontaneous. Because E is positive. Yeah. And then it says, write the balanced net ionic equation for the reaction between I2 and the solution that you selected in part E. So you're just showing the half reactions, right? Combine your two half reactions together. Because notice, these already are net ionic. They don't show our Na. So when you combine them, that shows your net ionic equation. I2 plus 2S2O32 minus yields 2I minus plus S4O62 minus. And the reason that that works out like it does is because notice it's 2 electrons and 2 electrons. So your electrons already balance out. Remember, your electrons have to be on opposite sides, right, in order to cancel them out. They have to be on opposite sides. If you notice that they're on the same side, then something didn't go right. Okay, and so free response question, this one, it brought a lot of concepts from Big Idea 3 in. This is what the rest of it looked like, and so this is what I mean by a lab-based question, where even if it doesn't say, like, you know, write an experiment, it still says that to determine the molar mass of an unknown metal, here's what you do, it's collected, here's the data, so it kind of shows you everything that's happening, but then it actually says calculate the number of moles, calculate the molar mass, and so this is what I would say to go through. Really just A and B. Oh yeah. So A and B, look at the scoring guidelines. I think we just did, what, E and F. And so just look at like A through D. Kind of work through it, see if you have any questions. But this was very much a Big Idea number 3 free response question. Okay, so that's it for today. But again, as you work through, if you're looking and you're like, oh, I need some more practice with, redox stuff, big idea number 3 in this review book ties everything that we just talked about in together. Same thing with like big idea number 2, when you look at solutions and gases and shapes, right? Drawing Lewis structures, intermolecular forces, that's all big idea number 2 from this book. All right, tomorrow's kinetics.